Exponential functions and equations review, math 30-1. And we're going to start off with graphs of exponential functions. So we have y equals 3 to the x. If you go to -2, it's 0.11111, because it would be 1 over 9. If you plug in -1, you get a third, so 0.333. 0, you get 1. 2, you get, or 1, you get 3. 2, you get 9. 9. And then these ones are just getting closer and closer to 0, but not touching it. They don't touch it because what's actually at the equation of y equals 0, because the x-axis equation is actually y equals 0, and the y-axis equation is x equals 0. So on the x-axis, which is the y equals equation, we actually have an asymptote. It's a horizontal asymptote because it's horizontal, and it's y equals 0 because that's the only way you can get a horizontal line is if it's a y equals line. Then we look at the half x. And we learned that if all we have is the base, it can instantly tell us if the graph is increasing or decreasing. So in this case, we have -3 and 8. We have -2 and 4. We have -1 and 2. We have 0, 1, 1 and 0.5, 2 and 2, 0.25. These are getting closer and closer to 0, but not touching. We'll pretend that went through. Wow, she's getting progressively worse. And we draw along the x-axis. And we have our exponential function. My computer's a little off. I should reset it. Anyways, our asymptote is still on the x-axis at y equals 0. And it's still a horizontal asymptote. So when you just have the base function without any transformation, if you're in the form y equals a b to the x, if you just have that function, if b is greater than 1, your graph is increasing. Like this one. If b is between 0 and 1, b can never be negative and it can never be 1. If it's just 1, then it's not increasing nor decreasing. You get, if it's between 0 and 1, you get a decreasing graph. Now that can change to an increasing graph if we actually reflect it in the x-axis, because if we actually reflect it into the x-axis, that red graph here, this really bad one I drew, would end up being an increasing graph. Okay, so those are just base functions, no transformations on it. So what's the domain of this exponential on the left? The y equals 3 to the x. The domain is XER because the arms go all the way to the left and they go all the way to the right, or negative infinity, positive infinity. The range, the entire graph is above the x-axis. So that's y such that y is greater than 0. It can't be equal to 0 because that's where the asymptote is. So it's greater than 0, not equal to. And how do you do that? Round bracket 0 to infinity. There are no x-intercepts because the asymptote is on it. The only way I'm going to get asymptotes is if my, x-intercepts, is if my asymptote moves off the x-axis. And my y-intercept in this case is 0, 1. I have a horizontal asymptote at y equals 0. And this graph, although it's decreasing, has all the same for domain, range, x-intercept, y-intercept, and equation of the asymptote. These are all the same. Because just because it's decreasing doesn't mean it is changing my range or my domain, or it's still not crossing the x-intercept. So the above functions have no transformations. Exponential functions have a horizontal asymptote at y equals 0 when the graph of an exponential equation has not been transformed. So if it's just a base function, it's at y equals 0. What is the only transformation of like vertical stretch, horizontal stretch, vertical translation, horizontal translation, reflections, which of those can move the horizontal asymptote? Well, if you have a horizontal line on y equals 0, if I move my graph to the right, or I move my graph to the left, it doesn't change my asymptote. If I reflect in the x-axis, it doesn't change my asymptote. If I reflect in the y-axis, it doesn't change my asymptote. If I stretch vertically, it just makes it taller faster, but it doesn't change my asymptote. The only thing that changes this asymptote is it has to be something that moves this asymptote up or moves this asymptote down. So the only thing that moves the asymptote is the vertical translation. And what's cool about it is the vertical translation is the asymptote, because your asymptote starts on 0 unless it's being moved. So wherever it's being moved to is your vertical asymptote. How can you determine where the horizontal asymptote is when you're looking at the transformed equation? It's just what the vertical translation is. The vertical translation is the horizontal asymptote. So if you have the equation y equals 3, 2 to the x plus 1 plus 7, the only thing that moves that asymptote off of 0 is the vertical translation. So my horizontal asymptote is now at y equals 7. That easy. My horizontal asymptote, therefore, is always at y equals the vertical translation. Always, for exponential. How can you determine the range of an exponential equation without typing the equation into your calculator? Well, your range on a basic function, no transformation, is going to be greater than 0. The only thing that can make it be less than 0 is a reflection in the x-axis. If I reflect in this, then my graph or my range will be less than the asymptote. So no reflection in the x-axis. And if I have a reflection in the x-axis, it's in front of my a value. No reflection in the x-axis, my range is going to be y such that y is greater than my horizontal asymptote, which happens to be my vertical translation, YER. And then if there is a reflection in the x-axis, my range flips. My graph is now down. So it'll be y such that y is less than my horizontal asymptote, which is actually my vertical translation, YER. Transformations of exponential functions. You can only compare exponential functions that have the same base. For example, y equals 3 to the x and y equals negative 3 to the 2x minus 4 plus 2. They both have base 3. Or we cannot compare them. So if they both didn't have base 3, I couldn't tell you what transformations happened. But because they have base 3, I can list the transformations. And that 3 doesn't affect a transformation. It doesn't give me a vertical stretch or a horizontal stretch or anything. It has to be the same. And the rest around it tells me what happened. So this, what I have to remember to do is here, I don't have a 1 in front of my x. So I can't even list my horizontal translation. So I would have to take that 2 out. Remember, we have to always remember to do that. So we get 2 to the x minus 2 plus 2. Okay? So we have a horizontal stretch because we have this 2 in front. It's a horizontal stretch by a factor of, and your horizontal stretch always flips, a half about the y-axis. I have a negative in front, so I have a reflection, and it's not with the x's, it's in the front, so it's a reflection in the x-axis. It's always in the opposite axis. I have a vertical translation 2 up because it's at the back, and a horizontal translation 2 right. If I forget to take that 2 out, though, I'm going to say 4 right, and I'm going to be incorrect. Okay, so we're going to look at the next example. Compare the functions y equals 2 to the x and y equals negative 3, 2 to the half x plus 4 minus 2. Determine the transformations that have occurred. So we can compare them because this is base 2 and this is base 2. Those 2's are going to do nothing to the actual question. They have to be the same or I can't compare them. So let's state what has happened here. I have a 3 in front. Before I deal with any of that, I still have this half in front of the x, and I need to have a 1 in front in order to get my horizontal translation. So that's the very first thing I'm going to do. I'm going to go negative 3, 2 to the half, x plus what? So I'm going to be dividing 4 by a half. When I divide by a half, it's like multiplying by 2. So I'm going to get x plus 8, then minus 2 at the back. Okay? So list the transformations. Well, I have a 3 in front. That 3 in front is a vertical stretch by a factor of 3 about the x-axis. It's always in the opposite axis. This half, I have a horizontal stretch by a factor of the flipped version, so 2 about the y-axis. I have a negative in front of the 3, so I have a reflection in the x-axis. This 2 at the back, I have a vertical translation 2 down. And this 8 here, I have a horizontal translation 8 left. And I'm done. So what's the equation of my asymptote? Well, we discussed this already. The equation of the asymptote on an exponential function is a horizontal asymptote. It's at y equals 0 unless it's been transformed. Up or down? Well, what moves it up or down? The vertical translation. So for exponential functions, my horizontal asymptote is always equal to y equals the vertical translation. Well, what is my vertical translation? 2 down. So my asymptote is going to be horizontal asymptote. It's going to be y equals negative 2. Boom. The domain and range. Unless it's a word problem, the domain for an exponential is XCR. The range, however, is either y such that y is greater than the horizontal asymptote or y such that y is less than the horizontal asymptote. And what makes that decision is, has it been reflected in the x-axis? If it's been reflected in the x-axis, that means it used to be up here, it's now down here, and I would have less than. So is this reflected in the x-axis? Yes. So because it has a reflection in the x-axis, it's not the greater than version, it's less than. And it's less than my horizontal translation, or my vertical translation, sorry, which is negative 2 YER. Now we need to know these without being just punching them into our calculator, because if we have a whole bunch of variables in the equation, you can't punch in your calculator, so you need to know your stuff backwards and forwards. They want the x-intercept of the new graph. So we would have x-intercept. You should instantly think y equals 0 always. Should be the first thing that pops in your head. So we're going to get 0 equals negative 3, 2 to the half x plus 4 minus 2. Now what we're going to do for this one, until we get into logs, is we're just going to go y1 and 2 for now, until we get into logs. Y1 and Y2. So y1 is 0, and y2 was negative 3 due to the half x plus 4 minus 2. Well, I have to put half in brackets so we know it's a fraction. A half x plus 4 minus 2. I'm going to go zoom 6 to get my standard window. And it's below, right? So I need to go this way so I can actually see it a little bit better. So I'm going to make my x-min negative 20. Now I have a horizontal asymptote running through 2. So this entire graph, shouldn't have used red on red here, should use different color. This entire graph is below the x-axis. So I'm going to have no x-intercepts. And when you think y-intercepts, you should think x equals 0. And because we have it typed into our calculator already, we're going to need to move down so that we can actually see where it crosses the y. So I'm going to do my y minimum. I'm going to make it be negative 50. Oh, and I finally see it crossing. So it's crossing here. So we just do second trace value because we know what x is. It's 0. And, oh, it's showing me my blue one. I need to take that one out. Second trace value, 0. And I get negative 50. So this is going to get 0 and negative 50. And logs will help us solve this stuff algebraically instead of with our calculators. Okay, our last example of transformation is determine the transformations that occurred between the function y equals 1/2 x and the function y equals negative 1/3 2 to the 2x minus 3 plus 6. Also determine the equation of the asymptotes and domain and range. Okay, we can't compare them right now. This one's a 2. This one's a half. The original is a half. So I need to get the new one to be a half as well. Remember, 2 is just 2 over 1. If I want it to be a half, I want it to flip. And how do I get it to flip? I raise it to the exponent negative 1. So I'm going to get y equals negative 1/3. This is just 2 over 1. So I'm going to get to flip to a half to the negative 1. And that negative 1 is just going to be multiplied by the 2 by the x minus 3. Because the 2 is already picked out, we can just literally put the negative 1 with the 2 and stop because we hit an end bracket. The moment we hit an end bracket, we stop distributing. And we don't want to distribute it all the way in, or else we're just going to have to take it back out to state the horizontal translation. So we have y equals negative 1/3, 1/2, negative 2 to the x minus 3 plus 6. So if they look like the same base, but one's a fraction and one's not, you just raise it to the power of negative 1 and it fixes it. Remember, it's just a reflection in the y-axis because if it was 2, it would be like this, to the 2x. If it was to the half x, it would look like this, right? And what are they just reflecting in? The y-axis. So that's why you get the negative with the horizontal stretch, like that. So what are the transformations? I have a vertical stretch by a factor of 1/3. Your vertical stretch is never negative because the negative gives you your reflections about the x-axis. And remember, when you're writing this out in an actual word problem, not in notes, you have to write vertical stretch. You can't write VS. You can't write BAFO. You have to write by a factor of, right? We have to write everything. Then we have a horizontal stretch by a factor of 2, it looks like, but remember we'll flip it. So it's a half about the y-axis. Both y's and x's are negated. So you have a negative here and a negative here. So we have a reflection in the x and y-axis. So it's supposed to be there. I'm just going to erase it. we have a vertical translation 6 up, which gives us our horizontal translation, or sorry, our horizontal asymptote. And then our horizontal translation is 3 to the right. So it's the opposite. So because our vertical translation is 6 up, our horizontal asymptote, which we don't want to short form if this is a real word problem, our horizontal asymptote is y equals 6, because it's normally at 0 and it's been moved up 6. The domain is XER. That doesn't change. Or negative infinity, positive infinity, depending on if you ask you for set, which is this one, or interval, which is this one. The range is going to be y such that y is less than, because I have a reflection in the x-axis, which is going to cause my graph to come down here, right? It's technically at 6, so it's going to come down here like this. So we are going to get an x-intercept, and we are going to get a y-intercept this time. We just don't have to find it. So it's going to be y is less than 6, YER. Then we did word problems. Oh, sorry. We didn't do word problems next. We did solving by common base. Then we did word problems. So in order to solve an exponential equation by common base, the base values must be able to turn into the same base, common base. If they cannot, you will need to use logarithms to solve the exponential equation algebraically. Remember, you can check your answers graphically using your calculator or substituting your x values you solved for back into the original typed equation and see if the left side equals the right side. You should walk away from these questions on your diploma knowing if you got them completely correct or not, just due to the fact that you can check them. Okay, so 8 and 4 I can make be base 2. So 2 to the 3 to the 3x equals 2 to the 2 to the 1 minus x, which I'm going to put in brackets so remember to distribute it. When you have one base and two exponents, you always multiply. So we're going to get 2 to the 9x equals 2 to the 2 minus 2x. Same base, we can set our exponents equal to each other then. Because if our base is equal, our exponents must equal. Solve for x, add the 2x. We get 11x equals 2. Divide by 11. X equals 2 over 11. So we're going to check this once in our calculator just to remind us how we do that. So we're saying the answer is 2 over 11. So we have 8 to the 3x equals 4 to the 1 minus x. I'm just writing it on my whiteboard so I remember what it is when I go to type it into my calculator. So it's 8 to the exponent 3x. And remember, if your exponent doesn't pop up on your calculator, if you have a TI-83 or a TI-84 that doesn't pop up and just gives that little hat symbol, you have to put your exponent in brackets. And then you have 4 to the exponent 1 minus x. I put in brackets because I felt like it. I didn't have to because my exponent popped up. So I press graph. And I have a wonky graph, but I can still see it because I have a wonky graph from before. But if I can see where they intersect, I can calculate it. So second trace, 5, enter, 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 and I take my x value. Now my x value is this crazy decimal. I got 2 over 11 as my answer. Well, what I can do is I can go second, quit, remember, or clear 800 times. You guys usually viciously hit clear so it goes away. If you just go second, quit, it brings you to this screen. And if you go x, enter, it brings up the x answer you just got. And then you could do math, enter, enter. And boom, 2 over 11, and I know I am right, and I move on, and I'm happy. And if I knew I was wrong, I'd go back, try again, right? Okay, so they get harder. B, what some people try and do here is they try and make them all be the same base, but one is 7 over 12, so it's going to be pretty hard to make the other ones be that same base. But because 49, and I told you guys to remember this, because 49 is to the 1 and 144 is to the 1, you can divide them. If either of them had an exponent with a variable, you would not be able to put them together. So like C here, we're not going to be able to divide that 2 into anything because the other two actually have exponents with variables. But the 144 and the 49 in B here don't. So I can divide the 49 over. So now I have 7 over 12 to the 2x equals 144 over 49. Now I know myself that 144 is 12 squared, and I know 49 is 7 squared. So this would actually be 7 over 12 to the 2x equals 12 over 7 to the 2. Now, they look the same, but they're reciprocals of each other. So if I raise the 12 over 7 to the negative 2 instead, so put a negative 1 up here, then it'll be 7 over 12. So I'm going to get 7 over 12 to the 2x equals 7 over 12 to the negative 2. And now I can solve it. 2x equals negative 2 divided by 2. X equals negative 1. I can check it algebraically by just plugging it back into the original. When I plug it back in for the x here, I'm going to get 7 over 12 to the negative 2, which is 12 over 7. And when you multiply them out, well, 12 over 7 to the negative 2, when you multiply by 49 and then reduce it, you get 144. So they do work. C. I have 1/4, which I can make be base 2. I have 2, which I can make be base 2. It already is. And 32, I can make be base 2. I cannot divide anything out because this one has an exponent and this one has an exponent. So that 2 is just going to stay as 2 to the 1. I would hazard you to always write it to the 1 so you don't forget it's to the 1. Because if you forget it's to the 1, you won't add the 1 and you're going to get the question wrong every single time. So I'm going to change 1 over 4 to 2 to the negative 2. X minus 12, and I'm going to put it in brackets so I remember to distribute it. And then I'm going to get 2 to the 1 times 32, which is 2 to the 5, bracket 2x plus 1. So I'm going to distribute that negative 2 in. So I'm going to get 2 to the negative 2x plus 24 equals 2 to the 1 times 2 to the 10x plus 5. Now this side, left side stays the same. The right side, I don't have one base with 2 exponents now. I actually have 2 of the same base with 2 exponents. So when I have 2 of the same base with 2 exponents, I add the exponents. So I'm going to get 2 to the 10x plus 6 because I go 5 plus 1. And now I have the same base on both sides, so I can set the exponents equal to each other. 2x plus 24 equals 10x plus 6. Add the 2x. 24 equals 12x plus 6. Subtract 6. 24 minus 6 is 18 equals 12x. Divide by 12 and reduce, and I get x equals 3 over 2. So it says here, why can you divide the two values in B, but you cannot divide the two values in C? You can divide the two values in B because both of the bases are to the exponent 1. Because in B, both of the bases have 49 and 144 are to the exponent of 1. Okay, last one. If we have the square root of 125, remember in grade 10 you were taught that the square root is just is to the exponent 1/2. So if I have the square root of 125, the index on 125 is 2, the exponent on 125 is 1. You drop the exponent underneath, or the index underneath, and you're left with 125 to the 1/2. So that's what we're going to replace the square root of 125 with. Whenever it's the square root, it's always to the 1/2. So 125 to the 1/2, 12x plus 4 equals 25 to the 8x plus 1. 125 to the 6x plus 2 equals 25 to the 8x plus 1. And then we can make them both be base 5. 125 is 5 cubed to the 6x plus 2 in brackets, so I'm going to distribute it. And 25 is 5 squared to the 8x plus 1. So we get 5 to the 18x plus 6 equals 5 to the 16x plus 2. Now we both have base 5, so we can set the exponents equal to each other. Subtract 16. We get 2x plus 6 equals 2. Subtract 6. 2x equals negative 4. Divide by 2. X equals negative 2. Now for the word problems that I said we were going to go to that we weren't actually. So the first word problem we went over was half-life, doubling, tripling. So if you read the word half-life, doubling, or tripling anywhere in the question, you are going to use this formula. So if final is F, I is initial, R is the rate, so if it's half-life, it's a half. If it's doubling, R is 2. If it's tripling, R is 3. T is the time to reach final, and P is how long it takes to half, double, or triple. It's the period. So if it says it halves every 3 minutes, then P would be 3. So if the amount of time follows directly after the word half, double, or triple, it's the P. P and P need to be in the same units. So if one's in minutes, the other one has to be in minutes. Those both exponents. So let's go through this. Example, iodine 131. 131 doesn't mean there's 131 iodine. It's just a value of iodine. It's like an isotope. So we just have iodine. Don't really care about the 131. I'm just going to cross it out so you don't try and use it. Has a half-life, so R equals a half, of 8 days. It follows directly after the word half-life, so it must be P. Determine the amount of time it will take. We're trying to find out the time it will take to the nearest day for the amount of iodine to reduce to 40% of its original. So they're asking us to find the time to reach final amount. And it says 40% of its original. It doesn't matter what you make the original be. If you multiply by 40%, it'll end up working out. So we're going to make our original, for me, I'm going to make our original be 1. So our initial be 1. Then our final is going to be 0.40 because 40% of 1 is 0.40. If you had made your initial be 100, then your final would be 40. It doesn't matter which initial or final you use because we're going to divide it over. I'm going to choose to use 1 and 0.4. When you go to solve any word problems, you can only be missing one variable. So we have to remember, if we're missing more than one variable, we need to go back, try again. Okay? Unless they're just looking for an equation that's not solved, then you could be missing more than one. So we have final, which is 0.40, equals initial, which is 1. Half-life, so R is a half, equals T, we don't know, over P, which is 8. I always tell you to divide your I over. I know in this case it's silly because it's a 1 and 1 isn't going to change anything, but I'm proving a point. So we get 0.40 equals 1/2 to the T over 8. And with logarithms, we'll be able to solve this. And we could try common base, but for now, we're just going to do y1, y2. So remember, if your exponent doesn't pop up, you need to write T divided by 8 in brackets. And your half has to go in brackets because the only way your calculator, doesn't matter if you have an old calculator or a new calculator, the only way it knows that it's a fraction is if it's in a bracket. So we're going to go 0.40 or 0.40, doesn't matter. And then y2 is going to be 1/2 to the power of x divided by 8. And like I said, whoops, I have too many x's. If that exponent doesn't pop up like mine, popping up, then you need to put it in the x divided by 8 in brackets. So we're going to go zoom 6. Now I'm going to second trace 5 and see if it works out. If it errors me, I need to make my x max bigger. So it said no sign change. So I actually am not seeing, with the window being like that, I'm not actually seeing where it's crossing. So I'm going to do 20. Now I can actually see it cross. So second trace 5, enter, enter, enter. And it's 10.57. No matter what it is, 10 point whatever, we're going to round up to 11 days because it won't be at least 40% of the original if we don't round up. Okay, so it's going to be to the nearest day, 11 days. And we always have to go back and check our rounding rules. It says nearest day. So we round up to 11. Not 10.5 or 10.6 or whatever. You can't go to the nearest tenth if it doesn't say go to the nearest tenth. If you do and you fill in a numeric response box like that, it's not going to work out well in your favor. Okay. We have 2 more left. Appreciation and depreciation. The only difference between the appreciation formula and the depreciation formula is if you're appreciating, you're increasing, so you're going to add the interest in decimal form. And if you're depreciating, you're going to subtract the interest in decimal form. And whatever's in that bracket is how much is left once you've done the 1 minus or the 1 plus. So final and initial F&I, the little I is the interest rate. It always has to be in decimal form, and N is the number of years. Okay, so here it says the population of a town is decreasing, so we know we're using this formula, by 2% per year. So I know my I is 0.02. If you want to turn percent into a decimal, you divide by 100. So 2% per year. The current population of the town is 11,568. So my initial population is 11,568. How long to the nearest year, so they want us to find N, will it take the population to be lower than 8,000 people? So my final is going to be 8,000. And it needs to be lower than 8,000. So no matter what time I get, I'm going to round up. So I have initial, or final, sorry, which is 8,000, equals initial, which is 11,568, bracket 1 minus 0.02 to the N. Now what I always tell you to do is divide your I over, so your window usually doesn't have to be as big. And I'm going to combine the 1 and the 0.02. So I'm going to get, and I'm going to leave this as 8,000 over. We don't want to turn this to a decimal and round it, because we can only round in the very last step. And then this can be 0.98 to the N. Now, this is 0.98. So that means that there's 98% left of the original. So that means that it went down 2%. So remember, we said that if that B value was between 0 and 1, that it was decreasing. So 0.98 is decreasing. So we go to plug that into our calculator. I'm just writing it down on my board so I don't forget the numbers. So 8,000 divided by 11,568, 11,568. And you could put that in brackets, but because it's by itself there, if you don't put it in brackets, it's not going to be the end of the world. And then 0.98 to the X. And we press graph, so zoom 6. And I'm going to make my X max bigger because I can't see where it's crossing. I'll make it be 20. I think I can see it now. Second trace 5, enter, enter, enter. And I get 18.25. 18.25, and I need to be below 8,000. If I round it to 18, the population isn't below 8,000, it's more. And I need to fall to below 8, at least below 8,000, so lower than 8,000, so I need it to be 19 years. Because it says to the nearest year. Our last formula is compound interest. The only difference between this and the appreciating formula up here is that I have CPs. Divide by CP times ICP. CP is the compounding periods. And you know that you use the first one, half-life doubling and tripling, if it says half-life doubling and tripling somewhere in the question. You know you use this formula if it has the word compounded somewhere in it. If it's just increasing or decreasing, but not half-life doubling or tripling or compound interest, then you use the appreciation or depreciation formula. So we have London invests $200. So that's my I. In an RESP at 3% per annum, means per year. I have to have it in decimal form. Compounded semi-annually, so CP is 2. Remember, if it's monthly, it's 12. If it's yearly, it's 1. If it's daily, it's 365. Quarterly, 4. Semi-annually, 2. It's how many times per year. Determine how long to the nearest month it will take for her investment to double. So her final needs to be 400 in order for it to double. And they want us to find to the nearest month. Remember that N always gives us number of years, so we're going to keep that in mind. So we're going to have final, which is 400, equals initial, which is 200. 1 plus 0.03 divided by 2 to the 2n, 2 times n. So if I go 0.03, divided by 2, I get 0.15. 0.015 plus 1 is 1.015. I'm going to divide by 200 over. That's what I always do. And so I'm going to get 2 equals 1.015 to the 2n. I'll write that on my whiteboard over here because I'm going to go to my calculator. And I'm going to y1, y2. Now remember, we're not going to be able to do this for life. This is just an exponential unit because we haven't learned how to use logs yet. So if they said algebraically, this wouldn't work. We would have to solve through logarithms. So we have 2, and then we have 1.015 to the 2x graph. Make the window a little bigger, 25. You can see where they cross. Second trace 5, enter, enter, enter. Now, that's 23.27 years. Okay? I'm not going to round that to 24 and then times by 12, because 24 times 12 is actually 288. Now my actual answer was 23.27777. I'm not allowed to round until the very last step. So is this the very last step? No. I need to take that decimal, multiply it by 12, and now I get 279.3. And I'm going to round that up to 280, not 288. So I can't round to 24, then times by 12. I have to multiply by 12 first and then round to my very last step. If at any point in time you're rounding before your very last step, you will get things wrong, or at least a chance to. So it's going to be 279.3, which rounds to 280 months. Takes a long time to double such a small amount. So that's exponentials. The next review I'm going to do is logarithms, which will use exponentials. And exponentials will use logarithms if we want to solve without just using y1 and y2 in our calculator. And you might be like, but I just want to use y1, y2. Great. However, when they ask you to do it algebraically, you have to know more than just y1, y2.